Hi everyone, welcome to the Methods 1-2 September lecture. My name is Major and I'll be taking the lecture today, but just before we begin, I'd like to talk to everyone about HR Notes. So HR Notes have been offering heaps of free resources to students across Australia since 2007. And the lecture that you're watching today, we've been offering lectures like these since 2015. Because the lectures that we offer are in line with our mission to help students as much as possible so that they have the best opportunity to succeed in their studies. We also offer a bunch of other resources such as study notes, lectures, online discussions, engaging online revision videos, newsletters, HR calculators, articles, and heaps more. So if you're interested in checking out these resources, please have a look at the info doc under the resources section of this lecture page. And if you have any other questions regarding these resources, please feel free to put it into the Q&A so that I can answer them for you. Okay, let's get started with today's lecture. So we have a lot to go through today. But just before we begin, I'd like to quickly introduce myself. So my name is Manjot Bulla. And I graduated VCE with an ATAR of 99.80, and I've been studying Bachelor of Biomedical Science at Monash, and I'm a maths and science tutor at Smart. And the subjects that I personally did throughout VCE were chemistry, maths methods, specialist maths, English, biology, and further maths. Let me know if you have any other questions. Otherwise, we'll get started with today's content. So today we'll be going over functions and transformations, calculus, and also a little bit of probability. So there will be no designated break in today's lecture. So pause whenever you need. And we will be using the Q&A software. So if you have any questions, please pop them through so that I can answer them. As I will be monitoring the chat during the course of the presentation. So feel free to ask me any questions so that I can answer them as they come up. Okay, so let's get started with the function side of things. So for functions, we're going to be looking at a review of linear and coordinate geometry, quadratic, circular functions, and inverse functions. So the overall aim of this lecture is to help you get started with the revision for the exam, and also act as a little bit of a head start for year 12. Okay, let's get started with linear equations, which is our first topic. So as you might already know, linear equations are a polynomial of degree 1. So the x variable here will have a power of 1, which will be the highest degree in the linear equation. And this is the general sort of equation that you will see. Y equals mx plus c, where m is the gradient of the graph, the gradient or the slope of the graph, which describes how steep a graph is, and c is the y-intercept. So the y-intercept is essentially what the y value is when the x value is 0. Okay, so there's a couple of formulas that you might need to remember. A lot of them are actually found in your formula sheets. So you will have to have them written down somewhere or memorized for your exam 1. So the first formula is finding the distance between 2 points. So on a linear plane, if we are given 2 discrete points, we can use this formula, which is a distance formula, to find the distance, the physical distance between these 2 points. So the distance formula is square root x2 minus x1 all squared plus y2 minus y1 all squared. And the way that it sort of works is it uses the principles of the Pythagorean theorem. So remember, Pythagoras is a squared plus b squared is equal to c squared. It's sort of using that principle to sort of come up with this formula here, where a, in this case, is the difference in the x values, and b is the difference in the y values. And instead of finding c squared, we're finding d squared. And then, to find d, we just square root whatever a squared plus b squared is. So that's essentially how this formula is derived. So just have to memorize this and apply this whenever you get a question asking about the distance. between 2 points. This sort of concept does come on the exam fairly often, so yeah, just definitely something that you just have to remember. Okay, sorry. Another formula that everyone needs to know is the midpoint formula. So the midpoint formula is essentially where you're finding the midpoint between 2 points. So when you're given 2 points on the linear plane, and you essentially have to find the x midpoint and the y midpoint. And the way that this formula sort of works is it sort of finds the average of the y values and the average of the x values. And that's essentially where the midpoint of the 2 points lies. So as you can see here, the x coordinate is just going to be the midpoint or the average of the two x values. So x1 plus x2 divided by 2. That gives you the average or the midpoint of the x values. And if you look at the vertical column, we can see we have y plus y2 divided by 2, which is the average of the y variable. So again, just another formula that comes up all the time in the exam. The next formula is the gradient formula. So if you're given 2 discrete points on the linear plane, you need to be able to determine the gradient of the line and ultimately the equation of the line. So the formula for the gradient, first of all, what does the gradient represent? Well, the gradient is just the rise over run, or essentially looking at how do the y values change as my x values increase or decrease. That's essentially what the gradient is referring to, or the slope of the graph. And basically we use this sort of principle of rise over run. Alternatively, change in y over change in x, which can be found by using this formula. So when you have 2 discrete points, so point A and point B, to find the gradient between these 2 points, you will have a coordinate system of x1, y1, and x2, y2. And basically, when you have this, you can then find out the gradient between these 2 points by using this formula over here. And y2 minus y1 just gives you how much is the y values changing by doing y2 minus y1. And in the denominator, x2 minus x1 will tell you how much your x values are changing. But in order to use this formula, you need to know 2 points on the graph. Alternatively, if they don't give you any points, they just give you a graph, then you need to identify 2 sets of points and then go from there. Okay, so here is just another sort of way of thinking about the gradient, which is tan theta. So we will come back to circular functions a bit later on, but as you might all remember, tan theta is equal to opposite over adjacent. So if we have an angle over here, the opposite is going to be the rise, whereas the adjacent is going to be the run. And essentially, tan theta is going to be opposite over adjacent, which is going to be rise over run. And we know that rise over run is equal to the gradient, or the m value. So that's why tan theta is often equal to the gradient. So if you know an angle, instead of knowing 2 points, you know the angle that the sort of graph makes with the, a parallel axis, of horizontal or vertical axes, or you might know this angle instead. You can then use that and tan theta to determine what the rise over run or the gradient is equal to. So another sort of concept that gets tested quite often. Okay, so now we'll move on to polynomials in general. So linear equations was a polynomial of degree 1. You'll also be required to look at and also sort of do calculations with polynomials of higher degrees. Usually it doesn't get much greater than a quartic. I've never really seen a question on the exam where they use anything above a quartic or a degree above 4. So you'll usually be seeing these three polynomials really often. So quadratics, where the highest degree is 2, cubics, where the degree is 3, and quartic, where the degree is 4. So all of these equations will look, also all of these polynomials will look a little bit different when you graph them, but they sort of have a general pattern, which we'll come back to in a second. But there are 3 different forms in which you can write the equation for all the polynomials. So you either have the expanded form as shown here, where you have, A, B, C. So you don't have any brackets essentially. So you have all the coefficients listed down in order of degree. So you have the highest degree and then, sequentially going to the lowest degree, which is x to the power of 0. So if something is missing, that's still a polynomial. It's still going to be a cubic if the highest degree is 3. For example, let's just say we didn't have bx squared. It will still be a cubic, but this time we just won't have anything with bx squared. So we're going to look at the highest degree to determine whether it's a cubic, quadratic, or a quartic. And the only information that the expanded form will tell you is the y-intercept. So any constants, for example, C, D, and E, are the y-intercepts of that particular graph. So this is the information that we can get from the expanded form. Next, we have the factorized form. So the factorized form is when we have, we factorize the polynomial either using a manual method or using a calculator. And this will look something like this. So we'll usually have a dilation factor. And then we'll have x plus something, x minus something, etc., etc. And this is called factorized form because essentially you're finding the factors of the graph. So x plus b, x plus c are the factors of whatever this quadratic is. Similarly, x plus b, x plus c, x plus d are the factors of this particular cubic. And what we can determine from this is the x-intercepts by using the null factor law. So essentially, let's say if we're just looking at the quadratic, we have a, x plus b, x plus c. And when we let that equal to 0 to find the x-intercepts, that will essentially just be x plus b equals to 0, thereby x equals to negative b. So that's one of the x-intercepts. And we also have x plus c equal to 0. And that will give you x is equal to negative c. So the factorized form is probably the hardest one to get into if you're just given an expression in, for example, expanded form. So most of the time you will be using a calculator, but you need to also be able to do it by manually, and that's usually through the polynomial division methods, which we'll have a look at a bit later on. And then the other form, so here is graphing. So here's a little bit of information about what the graph will look like when you're graphing it. So if you have a linear factor, so when you put it in factorized form and you have a linear factor x minus a, what that means is that at that point, so let's say we solved it and we get an x-intercept of x equals a. So at the point where the graph crosses the x-axis at the point x equals a, we're just going to have a linear line going through it. So that's what a linear factor tells you. A linear factor is basically where you have the power of 1. If you have a quadratic factor, what that tells you is that the graph actually forms sort of like a quadratic at that point. So it can either be a quadratic like this, or it can be a quadratic like this. But essentially, you approach that value and then you return, essentially. So whereas the linear, you're just going straight through it like a linear line. If it's a power of 2 for the factor, then you are doing a quadratic. We are forming a quadratic sort of thing. And then if you have a cubic, the graph essentially forms a point of inflection, or a stationary point of inflection to be more specific, at that particular point. So what this will look like is if you have a really big graph, something like, y equals a, let's say x minus b, x minus c cubed, let's just say, x minus d to the power of 6. So, another thing that you need to know is if it's an even power, for example, squared or to the power of 6, we are going to produce something like a quadratic at that particular point when it crosses the x-axis. If we have an odd power, for example, cubed to the power of 5, to the power of 7, so on and so forth, we're going to have a stationary point of inflection, except for positive 1. For example, here, so positive 1 is the only odd power that won't give you a point of inflection. Instead, it will just give you a linear line or a value that, or a line that sort of just crosses at that point. So this is how we sort of graph polynomials when we're given something in factorized form. Another form that we usually use is the stationary point form. So a stationary point form is essentially where the graph is giving us information about the stationary point of inflection. So for example, if we have ax plus b squared, and like I said, if it's squared, then the graph needs to form a sort of like a, a quadratic at that particular point. So it's at b, c, so therefore the turning point will actually be at negative b, comma c, and we'll explain why that's the case when we go to transformations. So therefore we will have a turning point at this point, depending on what a is. So that's what that will look like. So, so this point essentially just describes the turning point of the formula. So if a polynomial can be expressed in this form, so not all polynomials can be expressed in this turning point form, only some can. But if they can be expressed in this form, the polynomial will only have one stationary point, which will be at negative bc. So no other, turning points or anything like that, if it can be written in this form. Similarly here, we have a point of inflection at negative bc. Just draw that again. So if we look at the cubic now, we have a turning point at negative bc. So that will look something like this. So it's not really a turning point, it's more of a stationary point. Whereas for the quartic, it will look something like this, but it will usually be very sort of narrowish. But again, when you're graphing, it doesn't really matter. They'll look the same. So this will also look like this. Because of what I just mentioned on the previous slide, if you have an even power, it looks like a quadratic. If you have an odd power, it looks like a cubic. Okay, so now we'll look at the process of completing the square. So completing the square is essentially just a process that can be used to get something that is in the expanded form into the turning point form. And why we might need to use this is because, let's say we have an expanded form and we want more information. We don't know how to graph that function exactly, so we need to convert it into the complete the square form. And we can only do that for quadratics. We can technically do it for cubics and other polynomials, but it's not required for the VCE level. So here we have a turning point formula. So it's just going to be x plus b over 2 squared minus b squared over 4 plus c. So what is b and what is c? Well, if you have a polynomial function in the expanded form, y equals to ax squared plus bx plus c, well, the number or the coefficient in front of the x and the constant are going to be your b and c. So essentially you can just put it into this formula and you should get your complete the square sort of value. And a really good thing about when you complete the square is not only will you find the turning point, but it will also make finding the x-intercepts really straightforward and simple by just using simple algebra. Because you can't solve a quadratic equation by using simple algebra when it's in this form. However, when it's in this form, you can use simple algebra. Okay, so express the following quadratic in the form y equals ax plus b squared plus c. So the first thing that you need to do is you actually need to divide out the 3 here. Oops, sorry. So we need to take out the 3 before we do anything else. So we need to factorize the 3 out. So it's going to be 3x squared minus 2x minus 1 over 3. So now that we factorized, that out, what we need to do, now we can actually use the turning point formula. So when we actually do the turning point, we can either just straight away use the turning point formula, or we can look at, so what we need to do is we need to sort of make this a perfect square. So perfect squared is x squared minus 2bx minus b squared. Oh, sorry. Yeah, plus b squared. Plus b squared. So therefore, this in that formula, so x squared minus bx, or b here is actually 2. Oh, sorry, negative 2. So therefore, it will be x minus 1, which is b over 2, squared minus b squared over 4. So b squared is going to be 4 over 4, which is just 1, minus c. So that is essentially how you can put this into the turning point form. And then if you simplify it further, you will get y is equal to 3 x minus 1 squared. Negative 1 minus 1 over 3 is actually going to be 4 over 3. So therefore, it will be 3x minus 1 squared minus 4. So now that we have put it into the turning point form, let's go ahead and actually determine what the turning point will be. Well, it will just be this. So this is b. It will just be negative b. So negative b is negative 1, which is positive 1. And this c will just be c. So negative 4. So this is essentially how you can determine the turning point by using the expanded form of a quadratic. For cubics and other types of polynomials, you will have to use your calculator for that. Okay, so next we'll look at the quadratic equation. So quadratic equation is just an equation that is derived from the quadratic formula. So I've put the derivation on the right hand side, which you can have a look at, but it's not required. So derived from the quadratic formula, you can straight away find the x-intercepts of a equation, of a quadratic equation, if you know what the a, b, and c values is. And you can only determine that when it's written in the expanded form. So the quadratic formula is just x equals negative b plus minus b squared, square root b squared minus 4ac over 2a. Pretty straightforward, just knowing that, so this formula is usually not given in any type of formula sheet. So you have to memorize this or have it written down somewhere in your summary book. Okay, so here is an example of how we can use the quadratic formula. So basically, if we're given a function, for example, in this case, 2x squared minus 4x minus 3, we can easily determine the x-intercepts by just subbing in the relative values a, b, and c into the quadratic formula. So so the main thing I think about this formula is, first of all, the algebra itself. So going from here to here, That's the main important thing that a lot of students mess up if they're doing it by hand. Another thing that the students mess up is actually finding what A, B, and C is. So A here is going to be 2, B is going to be -4, and C is going to be -3. So now that we can determine it, it's so much more easier to just substitute those values into the formula. But obviously don't do it blindly. Know that sometimes you can make algebraic mistakes, and if you get a really weird looking value, then you might have made a mistake. But most of the time the values are weird, so sometimes it can be hard to judge. But just look at your algebra to see if you've made any superficial mistakes. Okay, so another thing that can be driven from the quadratic formula is the fact that if we have a square root, the number inside the square root will really determine if we have solutions or not. Because a property that you need to know about square roots is that any number inside of square root has to be greater than 0. If we have greater than or equal to 0. Because if we have a number that's less than 0, for example, -2, we can't take a square root of a negative number. So in that case, it's really important. So what that sort of derives is something called the discriminant. So the discriminant can straight away allow you to determine how many solutions a value might have. And what I mean by solutions is if you look at these graphs over here, solutions refers to how many times does the graph cross or intersect cross or intersect with the x-axis, because that's essentially what an x-intercept is. When and where is it crossing the x-axis? So if we have no solution, the graph might be completely above the x-axis. For something like, let's say, x squared plus 2. That is completely above the x-axis or completely below the axis. It will never even cross the x-intercept. So therefore, there will be 0 solutions or no solutions. And we have determined that in this case, the determinant or the discriminant, so the discriminant is essentially just the number inside the square bracket of the quadratic formula, or b squared minus 4ac. And we have determined that if there is no solution, this must be less than 0. Because what that will do is if we put this less than 0 into the quadratic formula, we will get an undefined answer, which is what we want. We don't have any solutions to begin with. If we are getting an answer, then that means that we've done something wrong, either in graphing or in terms of the algebra itself. However, if the graph has a turning point exactly at the x-axis, then we will have exactly one solution. And in that case, the discriminant will be equal to 0. Because if it is equal to 0, our values are just going to be -b plus minus 0 over 2a, which is essentially just -b over 2a, because plus minus 0 is the exact same thing. So therefore, only one solution if discriminant is equal to 0. Alternatively, if we have two solutions, what that means is the graph is crossing the x-axis. So it's going to cross or intersect at two separate points. And if it is intersecting at two separate points, the discriminant will actually be greater than 0, which makes sense as well. If it's greater than 0, we can have -b plus minus square root of that number, or so it can be plus that number or minus that number over 2a. So two different solutions. So a lot of the time, questions will give you a random equation that will ask you to determine whether there will be no solutions, one solution, or two solutions. Or they might give you a linear expression with a random variable, for example, and they might ask you to determine what that variable is if there is one solution, no solution, or two solutions. So here's an example illustrating what I just said. So here we have a quadratic equation, y equals x squared plus mx plus 4, where m is a real constant. And we are trying to determine the values of m such that the graph has exactly one x-intercept. So what that means is the discriminant. So first, you always relate these types of questions with the discriminant. So therefore, if it is exactly one intercept, the discriminant should be equal to 0. So x-intercepts will occur when y is equal to 0. So let's just first of all find what the x-axis is. The x-intercepts are. So if you want only one x-intercept, then we want the above equation to only have one solution. This means we want the discriminant to be equal to 0. So that's what we need to first of all identify. If it says one solution, two solutions, three, no solutions, we need to determine what the discriminant is going to be in that case. And then we just solve the equation as you normally would. So we have x squared plus mx plus 4. So you have your a value, which is 1, your b value, which is m, and your c value, which is 4. Sub it into the discriminant formula and let that equal to 0. And you should get m is equal to positive negative 4 as your answer. So I hope that makes sense. Again, let me know if you have any questions for the functions part of today's lecture. We're now going to be moving on to circular functions, which is, again, another topic that a lot of students struggle with throughout year 11 and year 12 methods. So a circular function is basically looking at a circle with a unit of 1. Or basically a radius of 1. Sorry, not a unit of 1, a radius of 1 units. So there are 360 degrees in a full circle. So there are two ways of measuring angles. So we're mostly used to degrees up to year 11. But now we will be introduced to another measure of angle, which is called radians. So radians, instead of measuring the angle between 2 points, it instead measures the radius. That sort of constitutes that angle. So if we have an angle of, let's say, 40 degrees, so that's essentially just describing this sort of angle over here. Whereas a radian actually describes this circumference distance over here. So what does this length actually measure? So that's the differences between a radian and a degree. Although this is sort of like very preliminary and you don't really need to know that for any type of sort of assessment. The main thing that you need to know is what's going to be on the next slide, and that's how to convert from degrees to radians. But just a little bit of an introduction to what a radian is. A radian is actually denoted by the small symbol, small c in the subscript, but often it's going to be ignored. So you're rarely going to see radians written with the c on the top. And they usually have pi in them as well, just because they're measuring the circumference. So for a whole circle, so 360 degrees, the radian equivalent for that would be 2 pi, because the circumference of a circle is essentially 2 pi r. And r in this case is going to be 1. So unless specifically told to answer in degrees, your answer in any questions in math methods always have to be in radians. So it's just an assumption that your answer is in radians. And as a standard value or an exact value. You never write your answer in decimals unless told to do so. So here are two really important formulas. Can also be done in your calculator. But essentially, if we're going from radians to degrees, we multiply the angle that we have. So whatever angle we have in radians, we multiply that by 180 over pi. So the thing about this is, if you don't remember the formulas, which one's which, well, you know that radians usually have 2 pi r in them. Pi in them. So if you want a degree, you want to remove that pi. So you need to multiply by something which has pi in the denominator to effectively eliminate that. So that's essentially how I memorize which formula to use and when, because you will never end up with something like pi squared. So you should never end up with something like this. That means you've done something wrong. And going from degrees to radians, we multiply the angle in degrees by pi over 180. Okay. So I'm just going to spend not a lot of time, but just a decent amount of time on the unit circle. So the unit circle is basically a circle which essentially has a radius of 1. And it's on the number plane, so the xy axes. We have a radian of 1, a radius of 1. So therefore, this point over here is going to be 1, 0, because the y value is 0 and the x value is 1. And essentially what the goal of this unit circle is to, let's say, determine any point along this circle, so the coordinates of this point along the circle, given that the only thing we know is the angle that it makes with the origin. So we only know what alpha is, and we have to determine what x and y are, what the coordinates that that angle would make with this point over here on the unit circle. So the way that we need to think about this is, first of all, finding what, this vertical length. So this vertical length is y for this coordinate point. And the x length is, obviously x. Another way of thinking about it is in terms of the angle. So this side over here is the opposite side for this angle, whereas this side is the adjacent side for this angle. Now, if we think about it in terms of sine and cos, we know that sine alpha is equal to opposite over hypotenuse. And what do you know? Hypotenuse is 1. So therefore, it's just going to be opposite. And what do we know about the opposite side? Well, it's just y. So therefore, sine of theta is equal to the y coordinate at this particular point. And for the cos, we can think about it in terms of adjacent over 1. So we can think about it in terms of adjacent over hypotenuse. And hypotenuse is just 1, so it's just going to be equal to the adjacent. And we know that the adjacent is equal to the x value. So therefore, sine of the angle is equal to the vertical length. Cos of the angle is equal to the horizontal length in a unit circle. And tan is just going to be sine, or the y value, over the x value at that particular point. So again, I hope that really made sense, but essentially the unit circle can be sort of simplified by this diagram over here. So basically, if we know the angle, we can determine what these coordinates are on the number plane by using cos of alpha and sine of alpha. So just quickly talking about the symmetry properties of the unit circle. So let's just say if you're trying to measure this, an angle at this point over here. So at this point, the x value, because we're on the negative side of the y-axis, the negative side of the x-axis, my x value is actually going to be negative. So it's going to be negative x. But my y value is going to be positive still. It's still going up or above the x-axis. So essentially, if I were to find what sine is equal to, and remember sine is equal to y, or the vertical length. So it's just going to be equal to positive y. So therefore, at this point, sine is still going to be positive. Whereas cos, which was the x length, is going to be negative because it's equal to negative x. And tan, which is equal to sine over cos, or y over x, is going to be y over negative x, which is going to give you a negative value. So therefore, we've come up with an acronym to determine which of the three trig functions is going to be positive or negative in that quadrant. So A means everything is positive in the first quadrant. F means that only sine is positive in this quadrant. T means that only tan is positive in this quadrant. And C means that only cos is positive in that quadrant. So all of the other, so sine and tan, will be negative in this quadrant over here. Because if we think about it, the x values are positive, but the y values are negative. And tangent is just y over x. So therefore it will be negative. Whereas in this case, both sine, so the x values and also the y values, will be negative. However, since tan is y over x and both of them are negative, the negatives will cancel out to just give you y over x, which is tan. Okay, and another thing that you need to know about the unit circle, it actually repeats itself. So it will go 2 pi, and then 2 pi, and then 2 pi, and then 2 pi, and so on and so forth. It can also go negative. So negative 2 pi, negative 4 pi, negative 6 pi, so on and so forth. So essentially, if we have found this value over here for the angle in the first rotation. So let's just say it is 150 degrees, for example. So if we add 360 degrees to the 150 degrees, we end up at the same point. So therefore, these quadrants, these coordinates will be the exact same as well. So therefore, cos and sine will not change, regardless of how many rotations you do. Even if you're going backwards as well. So you'll get negative angles, but your sine and cosine value will still be positive. So that's something really important to just identify when you're doing questions like this. So now we're going to be having a look at exact values quickly. So there are actually 3 ways in which we can memorize the exact values. So first is the hand method. The first is the table method, which I personally prefer. We also have the triangle method, which is kind of neutral. I don't really use that method. And then we also have the hand method. So the hand method, I personally don't know how to use in the most accurate manner. A lot of people do use it, but I haven't really seen many people use it. So table method is probably the best way of memorizing the unit circle. And I've included it here. So essentially what you need to do is, for sine and cosine, start off with, actually when you're doing the table, just start off with sine. You don't need to do anything for cos and tan. So what you need to do is you need to write some, just leave the numerator blank, just write numerator, which is blank, over 2 for each of them. So 0, pi on 6, pi on 4, pi on 3, pi on 2. So just leave the numerator blank for now and write over 2, over 2, over 2, over 2. Now what you need to do is, going from left to right, you need to do root 0, root 1, root 2, root 3, root 4, and stop at pi over 2. So this way, you will get the exact values that it is equal to. So I hope that made sense. Let me know if you need me to explain that again. For cos, it's essentially just the reverse. So you start off with the highest value, so root 4 over 2, then you go root 3 over 2, root 2 over 2, root 1 over 2, and then root 0 over 2. And then tan is just going to be sine, the top value, over the bottom value. So for example, for pi over 6, it's going to be half over root 3 on 2, which is going to be half times 2 over root 3, which is equal to 1 over root 3. So it's just sine over tan. So the main one that I would say is probably memorize just one of these. Cos should pretty much be the opposite, and then tan is just this over this. So that's essentially how you can use the table method to memorize the exact values. But I would say, if not by the end of year 11, then definitely before the beginning of year 12, have this sort of memorized so that you're not struggling next year and you can focus more on the more harder aspects of circular functions. So here is the triangle method. So again, you need to memorize 2 of these triangles. So you need to memorize this triangle and then this triangle and also the values. And essentially the way that this works is, for example, for pi over 4, you can easily determine what cos, sine, or tan pi over 4 is because you know what the opposite... why does it keep on going back? What the opposite, what the hypotenuse, and what the adjacent is. For example, if I was to determine what sine theta is going to be, pretty straightforward. It's just going to be opposite over hypotenuse, or 1 over root 2. But again, you will need to memorize this triangle as well as this one over here as well. So here is just an example of how we might do a question that asks us to evaluate a circular function. So let's say we're trying to evaluate sine 7 pi on 6. So the first thing that we will need to determine is what quadrant that lies in. And 7 pi on 6 can actually be written as pi plus pi on 6. So I already know that midway of the circle is pi. So it's a little bit more than pi. So therefore this is actually going to be in the 3rd quadrant. And since we're finding the sine value, and we look at the cast rule, sine is actually negative in the 3rd quadrant. So then what we need to do is, from 7 pi on 6, we need to find the basic or the principal value. And that's pretty straightforward. So if you have 7 pi on 6, it's just going to be pi over whatever the denominator is. So if you had like 7 pi on 3, it will just be pi on 3. If you had 7 pi on 4, it will just be pi on 4 for all of the values. So that's the principal value. So essentially what you're finding now is just sine pi on 6. But instead of it being positive sine pi on 6, it's actually going to be negative because this value actually lies in the third quadrant. So again, I hope that makes sense. So you're going to get negative half, and for that you need to use your exact value table or your triangle method. Similarly, if we have cos 2 pi on 3, first step is to determine what quadrant that is in. So cos 2 pi on 3 is actually in the second quadrant. And in the second quadrant, cos is actually negative. So therefore, if I'm trying to determine what cos 2 pi on 3 will be equal to, I need to first of all determine what the principal value is. And like I said, it's just going to be pi on the top over whatever the principal or whatever the denominator value is. So it's just going to be pi on 3. And again, since cos is negative in that quadrant, it's going to be negative cos pi on 3 to give me negative half. So again, I hope that makes sense. Otherwise, do pop any questions into the Q&A. Okay, so now we're going to have a quick look at sketching circular functions. So when you're sketching circular functions, there's a few key processes that you need to follow. So the first step is always to determine the amplitude, period, and gap. This will help you identify the shape of your graph. How wide or how narrow it is, which is given by the period, or how tall or and short it is, which is determined by the amplitude. And also the gap, like I'll show you in the next slide, will tell you where to place your important points and basically help you determine how your shape is going to look. So you need to label the axes. So once you've determined the gap, you need to label the axes with the gap points. So if the gap points are like pi on 4, you need to label the axes as pi on 4, 2 pi on 4, 3 pi on 4, 4 pi on 4, 5 pi on 4, so on and so forth, depending on what the domain is. And you'll always be given a domain, because otherwise your graph repeats itself for negative infinity to positive infinity. Next, determine the starting point, if not at 0, 0. So if it's not at 0, 0, there's been some form of translation. You need to determine the starting point either by subbing it directly into the function, for example, and then going from there. And then you need to calculate the x-intercepts. So the x-intercepts are really important to label, as well as the y-intercepts. So you need to be able to not only calculate the x-intercepts by solving, which we'll have a look at in a few slides, but also you should be able to sort of plot it onto the graph. And lastly, you need to sketch a smooth curve that passes through all the main points. So once you have your gap point, something like, maybe something like this, you need to connect it in like a smooth graph. Oops, my bad. Oops, where am I? Sorry, I am over here. So you have, 1, 2, 3, 4. So just bear with me while I draw this. Yep, so just make it really, make sure it's really curved and everything. Otherwise, if it looks like, something like this, that's, you won't get full marks. Okay, so here's an example of the function y equals 2 sine 2x minus 1. So first step, determine the amplitude, period, and the gap value, as well as the y-intercept. So once you've determined those, then you need to determine what your maximum and minimum values are. And to determine your maximum and minimum values, all you do is you take the constant, and then you plus minus the amplitude. So minus 1 plus 2 is positive 1, minus 1 minus 2 is negative 3. So then that you've done that, you've determined your initial starting point, you determine your lower values, your max and your min. Then you need to label the data points using your gaps. Your gap in this case was pi over 4. then you need to label the axes using those points. So, pi on 4, 2 pi on 4, 3 pi on 4, 4 pi on 4, so on and so forth until you fulfill the entire domain. And then the way that your circular function is actually going to work is actually going to start off from the middle of the max and min data points, then it's going to go up at one gap point, then back to middle in the next dot point, then bottom in the next dot point, and then up again in the next dot point. So that's essentially why we find the gaps. The gap is so useful in determining how my graph actually looks, and how it's sort of like structured and oriented. Okay, so now we'll have a quick look at asymptote, at the tangent function. So the tangent function, again, looks very similar in form to cos and sine functions. However, in this case, the period is actually going to be pi over n. Because if you remember back to the unit circle, tan was positive here and also here. So if this angle is the same as this angle over here, or relatively similar, there's no point in doing plus 2 pi, because you'll miss some of the values. So then we just do add pi to get to that value, and then add pi to get to the next value, and so on and so forth. Now, another thing that you need to know about the tangent function is, since it's defined at some of the values, namely at pi on 2, we will have asymptotes. And asymptotes are essentially a value that your graph is approaching but will never reach. And the way that you can determine where the first asymptote is, if there have been some form of transformations, is you let whatever is inside the brackets equal to that new first asymptote. Oh, sorry, not new. Your original asymptotes. Your original asymptotes are going to be at pi on 2 and also any odd numbers. So you need to let it equal to the original, so whatever's inside the brackets, let it equal to whatever is inside the original, and that will give you the new the new first asymptote. So here is what the tangent function will look like. So for sketching tangent functions, it's important that we have vertical distance between the period and the first asymptote, that we also sketch asymptotes, add or subtract the periods of time to find more asymptotes, and that we also draw for the entire given domain. We also need to make sure that the x-intercepts will be halfway between asymptotes. So your turning points, wherever that may lie, have to be halfway between between the asymptotes. And lastly, you need to sketch the graph. So in terms of sketching the graph, what's important here is the curvature. So having the curvature, and also the fact that it's approaching the asymptotes and doesn't intersect or touch the asymptotes. So here is a quick example that I'd like everyone to have a go at. I'll just give everyone a minute. So if you're watching this online, have a go at this question, and then unpause to go through the solutions. Okay, so hopefully you've had a chance at this question. So if we have a function y equals tan x plus pi, x over 2, and we need to sketch that function in the given domain negative pi to 4 pi, first step first is to determine the amplitude. So the amplitude for the tan function is actually a little bit irrelevant, because the graph extends from negative infinity to positive infinity every single time. So I'm actually going to ignore the amplitude. But what I will find is the period. The period is going to be, so since it's tan, it's just going to be pi over n. So n was x over 2. So if you do this, you should get, let me see. Oh, sorry. Not pi over 2, what am I doing? It's pi over whatever the number is in front of the tangent. So it will be pi over half. which is equal to 2 pi. So again, I hope this makes sense. Once you've found the period, the next step is to then determine the gap. So the gap will just be the period, 2 pi, over 4. And this will help me determine where my data values are going to be on the graph. And the next step is to determine the asymptotes. So the asymptote, remember, we just let it equal to the original asymptote, whatever is inside the bracket. So x over 2 is equal to pi on 2. So that was the original asymptote if there were no transformations. So therefore, x is going to be 2 pi over 2, which is essentially just pi. So again, I hope that makes sense. So this is the first asymptote in this graph. So if I were to sketch it somewhere, okay. So now that I've drawn pi, I'm just going to label my axes quickly. I need to draw it for the given domain. So negative pi to 4 pi. So my asymptote is actually 1 pi unit, so 1 period apart. So for the next one, we'll be at 2 pi. And then the next one will be at 3 pi and 4 pi and so on and so forth. Similarly, if we go backwards, it will be at pi. Then it will be at pi minus pi, which will be, sorry, I'm doing the gap correctly, 2 pi over 4. Or 2 pi on 2. Sorry, it was pi on 2 the whole time. So it's pi plus pi on 2, which is 3 pi on 2. 3 pi on 2 can then further be converted into 5 pi on 2, but we'll go back. So pi minus 3 pi on 2. So this will give us x equals pi minus pi on 2. That will be 3 pi on 2. And then we can also go further back if we need to, but I believe that we don't need to go back. And in terms of the x-intercepts, they're usually also the period apart. So we have a right here. Oh, sorry, what am I doing? A point here to begin with. So this will be one of those x-intercepts. This graph will look something like this. And then I add pi units to get to the next one. So 0 plus pi is going to be, the period. Sorry, not the pi, the period. Again, really confused. Sorry. So we add 2 pi. So we'll get 0 plus 2 pi will give you 2 pi. I think I've done this wrong. Let's check though. Okay. Sorry, I don't know why I just did pi. So it's actually period, whatever the value is, plus the period, which is 2 pi, not just pi. So again, a big source of confusion, so have that cleared as much as possible and try to work through evidence to see if it makes sense. So therefore, it will be x equals to 3 pi. Remember, we have a 2 pi catalyst. And then we have this value right in the middle, which will give me this graph over here. So again, I hope it makes sense. And we actually haven't finished. So we need to have something over here. Oops, my bad. Remember, it has to be approaching that value. So something along the lines of this. Okie dokie. So that's essentially it for graphing of the tangent functions. Sorry, did I draw this wrong? No, sorry, that should not be correct. It should be like this instead. The other one that I draw was if there was someone sitting in, so that would have been if the gradient was, negative 3 pi onto to 4 pi. But if it isn't, just do negative pi, and so on and so forth. So here is what the graph might look like. Again, like I said, amplitude is not important. What is important is the first asymptote, the period, potentially the y-intercept as well. Okay, so now we'll move on to functions. So first we'll have a look at one-to-one functions. So there are many different types of functions, but a one-to-one function is essentially a value which, an equation which does not repeat any y values. And the way that we determine that, not algebraically, but graphically, is by looking at the horizontal line test. So the horizontal line test is essentially where we are determining whether the function is one-to-one. So if we draw a horizontal line at any point during the graph, it should give us a only one intersection, such as is shown in this graph over here. So essentially what I'm saying is it should have each x value corresponding to one y value, not multiple. Alternatively, we can have a not one-to-one graph where we do the horizontal line test, but it does not give us a single intersection. There's going to be multiple intersections. Does that make sense? I hope it does. Otherwise, please pop it into the Q&A. So another definition of the inverse function, besides swapping of the y and x, is the fact that it is actually a reflection in the graph y equals x. So if we look at this line over here, these two graphs are actually going to be symmetrical. So they're actually going to form a plane of symmetry. So this is the plane of symmetry. So what this is going to do is, if I flip it on one side, is actually going to give me the inverse graph, because essentially what's happened is the x and the y values have been swapped. Another way to think about the inverse function is that a function takes x values and turns them into y values. The inverse of that function could then be taken from those y values and turn them back into original x values. But the way that I like to think of it is sort of like a machine. So we have the x values chugged into a machine to give us y values. And those y values get chugged into the inverse machine to give us x values. So that's essentially how the inverse functions essentially work, and also what they mean. But in terms of VCE, you need to be really aware of their sort of notation and convention. So for a function f, the inverse function is notated as f inverse. A lot of people, or a lot of students, get this confused with 1 over f. That is completely wrong. 1 over f is 1 over f, f to the power of negative 1, or f inverse, is f inverse. So when you have been given a short answer question which asks you to, prepare dinner, or, sorry, what am I doing? So when you have been given a question that asks you to determine the inverse function of f, what you will need to do is, first of all, let y equal to f of x. So once you let y equals f of x, you need to actually say let y equals f of x if it's not already given in the form y equals f of x. But once you have written this sort of notation, the next thing that you need to write is to invert, swap x and y. So again, something you need to write just in terms of notation. And then you need to rewrite the equation y equals f of x, where the x and y are swapped. So for example, let's say the original function was y equals x squared plus 6. My new value will now look something along the lines of x is equal to y squared plus 6. So that is what my function will now look like when I swap it, but I will obviously need to rearrange to make y the subject. So that's the last step. To make, that's the fourth step. Rearrange the equation to make y the subject. So it should be pretty straightforward. Obviously, most of the questions will allow you to use your CAS, but if they don't, it can be easily done on your by hand as well. And lastly, you might want to define what f of n inverse is by saying something along the lines of y is equal to f inverse of x, and so on and so forth. So another thing that's important in this case is sometimes the question will ask you to define the function. So if you're defining, remember this specific notation. So you have f inverse, then the two dots, then you have the domain to the codomain, and then you have what the f of inverse of x actually equal to. So just make sure you really read the question. If it hasn't asked, I would still probably give my answer into this form as well, because sometimes they are assessing for the domain. Okay, so here is an example. Consider the function g, 1 to infinity, and here we have an equation. G of x is equal to 4x minus 3, x minus 1. So what we have to do is determine the inverse function of g. So we're finding g inverse of x. So first step, for inverse, we write these two steps first. So write this notation, and once we've done that, then we can start doing the algebra. So here I've actually written down what I've done to solve this question and get to the final answer. So first we have x equals to 4y minus 3 over y minus 1. So I've swapped the x and y variables. Alternatively, what you could have done is simplify this expression first before, substituting x or swapping x and y. So in this case, what has been done next is we've split the fraction. So we get x is equal to 4y minus 4 plus 4 minus 3, which gives me x is equal to 1 over 4y, 1 over y minus 1 plus 4. Next, what we can do is we can move the 4 to the other side, and then we can move the x minus 4 in the denominator and swap it with the y minus 1 and rearrange to make y the subject to give you g inverse of x. So really, a really crucial process that comes again and again in exam 1. So you should be really familiar with how to go from the normal to the inverse. Okay, so let me know if you have any questions for that part of this today's content. But otherwise, we'll move on to transformation. So just to briefly summarize, a transformation is actually where we are changing the x or y variables of a graph in order to, So essentially, we just change the x or y variables of a graph, either by reflection, translation, or dilation, where dilation is just stretching or contracting the graph. And this could have a variety of uses in terms of using maths for modeling, for example. So there's quite a few methods for doing the transformations. I personally use the coordinate method. So the coordinate method will take a little bit longer, but you can be 100% confident that if you've done all the steps correct, you will get to your correct answer. So the way that you do the coordinate method is once you've been given a transformation, you write it in this sort of like coordinate method. So x, y gives you or transforms into, something. And then you start applying the transformations in the order in which they are given. So first, it's a dilation from the y-axis. So if it's a dilation by a factor of a from the y-axis, we know that if it's a dilation from the y-axis, it actually impacts the x values. Because if you think about it, let's just do a cubic. Oops, that's not a good cubic. Actually, let's do a quadratic. So for this quadratic, if I have a dilation from the y-axis, which means my graph is being stretched this way or contracted this way, my y values remain the same. It's my x values that are changing at those particular points. So therefore, we put it in front of the whatever the dilation factor is, we put it in front of x. Similarly, if it's from the x-axis, then we put it in front of the y. So it's a bit of an opposite effect. Next, if we have reflection, same thing here. If it's in the x, then we put it in the y. If it's in the y, we put it in the x. And then we finally do the translation. So C units up. So we put, so up is changing the y values. So therefore we put it as plus C at the end. And D to the right. So therefore we do plus D. Next step is to write what x dash and y dash is equal to. So whatever's in this coordinate is essentially just x dash and y dash. So this is essentially what x dash and y dash are. So what we can do is we can let x dash is equal to this coordinate, y dash equal to this coordinate, and rearrange for x and y. So once I've rearranged for x and y, such as shown in the last step over here, then I can immediately sub that into the equation. And once I substitute x and y into the equation, I should get my new transformed equation. Okay, so now we're essentially done with the transformations. The transformation was pretty short. It was just looking at the coordinate method. That's pretty much all that's required for year 11. But now we'll move on to calculus, and specifically looking at average and instantaneous rates of change, as well as turning points and stationary points. So first, let's have a look at what a rate of change actually is. So rate of change is basically a way of describing the gradient of a function. So it's sort of similar to linear equations that we looked at before. But for a linear equation, the gradient was actually uniform. So what I mean by that is, if we have a linear equation, the gradient at this point is the same as the gradient at this point, or the slope. However, graphs like these, the gradient is constantly changing, throughout the graph, because it's not linear. So a rate of change is going to be a way of describing, how my y values change as my x values change, which is essentially what the gradient or the m represents. So there are two types of gradients that we need to be familiar with. So we have the average rate of change, which investigates the average gradient between 2 points. Or we can find the instantaneous rate of change, which we'll come back to in the next few slides. So the average rate of change pretty much works in the same way as the gradient formula for linear expression. So y2 minus y1 over x2 minus x1. The only difference here, so that only works when you're given 2 discrete points. Sometimes what you might be given is the x values and the equation of the line. So if you have the equation of the line, you can easily substitute it in to find what the y value and what the y values are going to be, and then from there on you can use the average rate of change formula, which is just the gradient formula. So pretty straightforward for average rate of change. Next we'll look at tangents and also instantaneous rates of change. So if you think about a tangent is just a straight line that touches a curve once. But a property of the tangent is that it's going to have the same gradient of the point that it touches at that particular point. So at this particular point, the gradient of the tangent and the gradient of the circle is actually the same. If it wasn't the same, so let's say the gradient of this line was something else, it might look like this. That's not a good representation. It might look, So if it wasn't the same, it might look something like this. But are we determining the average rate of change here or the instantaneous rate of change? Because remember, the tangent here will have the same gradient and also will touch the curve once. But if we deviate this gradient, even by a little bit, it's going to now potentially touch the gradient at that point, which is essentially what we don't want. So if a gradient at point x1, y1 is m, then the gradient at that point is going to be, so pretty straightforward, just another formula derived from linear expressions to determine what the y value is going to be if we know the x value, if we know the x values and the gradient, or we know a pair of coordinates, so just one coordinate and the gradient. So and this formula I always use. So if I know what the gradient is, what one of the x values and what one of the y values is, I can just use y of t or y of the tangent or the gradient of the tangent. Sorry, not the gradient. The equation of the tangent is equal to the gradient, bracket x minus x1 plus y1. So once we've actually determined what the gradient is going to be at that tangent point, we can easily go ahead and determine the equation of the tangent, so the equation of the actual line that is going to be, intersecting the graph at one point. But what you need to know about this is it's not only going to show the coordinates at this point, it's also going to show the gradient. So that's going to be the same. Okay, so next we'll look at normals. So normals are essentially just the opposite of tangents. So basically a normal line is perpendicular to the tangent and passes through the same point as the tangent. So what that means is at that point, instead of having a line that has the same gradient at that point, we now have a line that goes perpendicularly through that point with a gradient that is a negative reciprocal of the tangent gradient. Okay, so what that might look like is, let's say we have m1 being the gradient of the normal, but we've already found the gradient of the tangent by finding the instantaneous rate of change, or calculus, which we'll have a look at in a second. Once I've determined that, what I need to do is use this formula over here. So m2, or the gradient of the normal, is going to be the gradient of the parallel line, or the tangent. It's just going to be the negative reciprocal of that. So -1 over the gradient of that line, of the tangent line, sorry. And the way that you determine the equation is pretty much the same sort of process. Yn minus y1 is equal to -1 over m x minus x1. So the instantaneous rate of change tells us the exact gradient at an exact point on a curve, like I've mentioned before. So before, when we were looking at the average rate of change, it was between two discrete points on the graph. Now, from the average rate of change, we've actually defined the instantaneous rate. So it's the rate of change at, let's say this point by itself. Now that's really hard to determine because if we have 2 points, we have 2 sets of coordinates to work with. But if we just know one point and we know where it lies on the graph, there's literally nothing else that we can do to work out what the gradient is going to be at a particular point, unless using something called calculus and differentiation. So that was just a brief difference between the instantaneous and average rates of change, and also their properties. Okay, so now we're going to be looking at the concept of a limit. So a limit is essentially a value that a function approaches as the input approaches some other value. So essentially, a knowledge of limits is not required in too much extensive detail in the methods course. However, essentially what this expression, or this limit expression, is essentially telling you is that as my x values approach p for the graph f of x, my y values are approaching L. So that is what that is going to tell you. And essentially that's what we want. So if we are trying to determine the instantaneous rate of change from the average rate of change, we want to find, 2 really close points, and we want to determine the gradient between them, because that's going to be much more accurate as opposed to having really far away points. So essentially my difference between these 2 points is approaching 0. And that is essentially the derivative. However, there is the first principles method that you do need to know in a little bit of detail, but not too much. And it really won't come that often in the exam. But just know that it is actually derived from the quadratic form. Sorry, not the quadratic. It is derived from the average rate of change formula. So really just be aware of that. But what we're doing here is, let's just say we have, we want to determine the instantaneous rate of change, so the rate of change at that particular point. for x is equal to a. So what we might do is we might work out the gradient just how we normally would. So we're just going to let this distance between a and another point, a plus h, so a plus an arbitrary number, and just find the gradient. So it's just going to be f of a plus h, so whatever the y value is at that point, minus the y value at a, f of a, over this point, a plus h, minus a. But remember that a plus h minus a is just going to be h. So that's how we get the limit formula. And what we want is the h value to essentially approach 0. So you want it to be as close to 0 as possible so that we can find what the instantaneous rate of change is. So that's why we let the limit h approaches 0 of the average rate of change function. So again, I hope that made sense in terms of how the instantaneous rate of change has been derived by first principles from the average rate of change. Okay, so now we're going to be looking at the different types of notations of derivatives. So first we have just the normal Lagrange's notation, which is just y equals f of x, and the derivative being y equals f dash x. So pretty straightforward. You're going to see this 99% of the time. Other times you can also see Leibniz's notation, which is y equals f of x, and then dy on dx gives you the derivative. So as opposed to f dash x, it's going to be dy on dx. And then we lastly have Newton's notation, which you will not see in methods whatsoever. But I've just put it there just in case. So the Newton notation is essentially where you have a function and the gradient is written like y dot. Essentially, is just another type of, so all three are different types of notations, but depending on what the question is giving you, so if the question is giving you, f of x is defined as blah, 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 then you will use Lagrange's notation. So the derivative will be f dash x. However, if your answer is given in the form of y equals, something, then it'll be in the form of Leibniz's notation, which is dy on dx. So I have included an example for the differentiation by first principles, but I won't be going through this example in too much detail. However, it is in the slides, so if you would like to check it out, please do so from the resources section of this lecture page. Otherwise, we will look at just basic differentiation. So there's a few rules for differentiation that you need to follow, but the basic rule here is that the derivative of any polynomial is essentially a dropping of the power and then subtracting by the power. So therefore, the derivative of f of x is equal to x to the power of n is equal to f dash x, and here we're using the Lagrange's notation, is equal to n, so I've dropped the n down, x to the power of n minus 1. So here are some other rules that you might come across when doing calculus, and that is the coefficient rule. So if you have a function and then you have a coefficient at the front, or you factorize something, you can move it to the front without affecting your derivative. And then when you find what d dx f of x is equal to, you just multiply the answer by a. Pretty straightforward. Just a minor trick in order to get, improve your efficiency in the exam. Next, if we have the addition or subtraction of two functions. So essentially what we just do is we derive f of x separately and we derive g of x separately, and your answer is just going to be f dash of x plus g dash of x. Next, we have the derivative of a constant. So the derivative of any constant is always going to be 0. And this is because we imagine that we just have a constant line, so therefore there's no real gradient whatsoever. Okay, so here's just a really quick practice question to find the derivative of the following functions. We have 3 over 4, 4x to the power of 4 minus 1, plus 5 multiplied by 2, x to the power of 2 minus 1 plus 0, And this apparently is equal to 3x cubed plus 10x. We'll have a look at how we might solve this. So we're just going to simplify this. So this and this is going to cancel out. So we're going to get 3x. 4 minus 1 is going to be 3. And then lastly, we have 5 times 2, which is 10x. 2 minus 1 is just going to be 1. So therefore, the answer here is, like the solution I've suggested, is just going to be 3x cubed plus 10x. Okay, now we'll look at stationary point. So stationary point is just a point on the graph where the gradient is 0, essentially. So that's why it's called stationary, because it's not moving. But f dash of x is going to be equal to 0, or dy dx is going to be equal to 0 at the point where we have a stationary point for the derivative function. So tangents at the stationary points are parallel to the x-axis. And that makes sense as well. If you have a gradient of 0 at a stationary point, your tangent is obviously going to just be a straight line, so it's going to be parallel to the x-axis. We can have 3 main types of stationary points. We can either have local minimums, local maximums, and also points of inflection. So most of the time, questions will be concerned with local maximums and local minimums. So tangents at stationary points are parallel to the x-axis, like I've established. However, if we have a vertical point, it's going to be undefined. So again, just really being familiar with, the local minima and local maxima and how they look is really important for these types of questions. So there are 3 methods mainly for determining the nature of a stationary point. So either using the first derivative method and drawing up a nature table, or we can do the second derivative method. So second derivative method is more so special, but it can be still used in methods to get full marks. However, I won't be using this method today in order to avoid any confusions. But we can also have knowledge of function shape and sketching. So just knowing how the function looks or behaves, we can also determine the shape of the graph. So here we have a derivative, and we're trying to determine the stationary points here as well as their nature. So what we do straight away is derive the function. So we have the function x squared plus 2x minus 3. We can derive that function and we will get x squared, x plus 3x minus 1. And then we can solve it to give us negative 3 and and positive 1. So negative 3 and positive 1. Next thing would be to determine what the gradient is at that point. So if the gradient is point, we use a slope table to give us a positive line at that point. However, if we have a negative gradient, such as that f dash is equal to 0, then we will draw a negative gradient like this. However, if it's equal to 0, then we can draw something like this, which is a straight point. Oops, sorry, what did I do here? It was supposed to be here. Yeah, but overall, this is how the nature table works. And overall, you can sort of determine, there's a local maxima at x equals -3, a local minima at x equals, +1. So again, I would say drawing up a nature table would probably be one of the best methods to find the local maxima and local minima, as well as any other stationary points. So we also have the second derivative method, which I will not be going through as it's not accessible, but I've listed down an example question of how to use the second derivative method for everyone to review, and I've also included some rules for the second derivative. Okay, so now we'll have a look at the recognition method. So recognition method involves a really good knowledge of the function itself. So if you have functions such as this one, which I can straight away tell that it's going to look something along those lines, I can straight away tell that the coefficient of x cubed is going to be positive, and therefore we're going to have a positive cubic function. So in a positive cubic, the first tertiary point must be a very relaxed, and the second tertiary point must be a local minimum for this particular graph. So again, just using the knowledge of your graphs is probably a little bit difficult, so therefore I usually always use my nature tables, which are the best method to use in an exam scenario to avoid making any mistakes. Especially if you don't have a calculator for exam 1. So next we have this concept of absolute maxima and minima. So absolute maxima and minima is just the absolute highest and absolute lowest value of a function. So they're different to local maxima and local minima is because we can have values higher than the local maxima or values that are lower than the local minima just due to the nature of the graph. However, absolute maxima and absolute minima are essentially just, the absolute greatest and absolute lowest values in a particular graph. And they can either be local minimums or endpoints, or they could be local maximum or endpoints as well. Okay, so here is an illustration of the concept of absolute maxima and minima. So if you look at the first graph over here, we can clearly see that the point that is the highest is this value over here, although we have the local maximum being at this point over here. Local minima, I can clearly see that it's not going to be this value over here because I have a value that's lower going down here. So therefore, in this case, this is my absolute maxima and this is my absolute minima. So again, like I said, it depends on the question and what you are given. In terms of what the absolute maxima and minima is. But if you are determining it by hand, you need to have determined all the endpoints and all the local maxima and minima in order to judge which one's going to be the greatest or lowest. So in the second graph here, we have this being the highest point. So therefore, we have the local maximum being the absolute maximum as well. And I can clearly see that there's minimum values going further down. So therefore, that's going to be the absolute minima. So here is a bit of a practice question, or an application question more so, about calculus and absolute maxima and minima. So if you're online, please have a quick go, or if you're not watching this as a live stream, have a quick go at this question, pause, and then we will go through the answers. Otherwise, if you're watching it online, we will go through the solution. As a live stream, we'll go through the solutions now. So we have Trig, a farmer who is building a fence against a wall. He has 20 meters of fencing and is thinking of making a rectangular area. So the question asks, what are the dimensions that will maximize the area covered? So essentially, we want to have the maximum distance covered. So we want the greatest x and the greatest y values, but overall, they should make up the largest area. So what we can do is we can formulate an equation. So the first equation that I can think of is that x, so 2x plus y, is equal to 20. Because the total fence used is going to be over here. So you have x on this side, so therefore x must be on this side as well. And we have y, which should be, just y. So therefore, 2x plus y is equal to 20. So this one is correct. Next, we can formulate a second equation for the area. And we know that the area is going to be x times y. We already know what x is. It's just x. Whereas y, we have determined this in this equation over here. So y is going to be 2x minus 20. So therefore, area becomes x brackets y has been replaced with 2x minus 20. And now we have a much easier equation to derive and solve. So straight away we will find the first derivative. So that will just be 4x minus 20 equal, and then we let it equal to 0 since we're finding the maximum and the minimum values. So if we let it equal to 0, we get x is equal to 5. And therefore the y value must therefore be equal to, if we put x back into the formula, we should get y is equal to 10. So this is how we can solve an application question like this. But yeah, so that was essentially the end of the calculus section of today's lecture. We'll now move on to probability and have a look at some of the conventions and definitions. So what is probability? Well, probability is just the chance of a certain event occurring when you know what the different outcomes are. So essentially, consider a scenario first of all. And the scenario is that you're throwing a fair six-sided die. The die can, when you roll it, it can give you different numbers, but it will be the 6 different outcomes for each side of the die. The sample space, therefore, describes the possible outcomes that we can get, which would be obviously 1, 2, 3, 4, 5, 6, which are all the numbers in the in the die. And we denote any values that we're listing in curly brackets. If we were listing the sample space as 1 to 5, but that will include every single decimal value between 1 and 5, we want to use the squiggly brackets here. So squiggly brackets we only use when we're sort of denoting something, or usually listing something, as opposed to giving a range. So that's actually what a sample space is, all the possible outcomes that can happen. Whereas an event is a group of specific outcomes. So an event for drawing or rolling a six-sided die is landing on an even number, or landing on an odd number, for example, or landing on a number that's the top 3, or something along those lines. So an event is just a group of possible outcomes from your overall sample space. So again, just basic definitions. Here are some notation elements. So we have this upside down U symbol, which is called an intersection. And it's actually read as A and B, or A intersection B. I usually just say A and B because this is essentially what it means. And we'll have a look at that in a coming slide. A and. So essentially what it does is it lists all the outcomes that are common to both A and B. So common means it must have elements of A and elements of B. So for example, rolling a six-sided die, so that's the experiment. Getting an even number and getting a number that is a multiple of 3 are 2 events. A and B would be anything that's common to both. So that would be, the number 6, for example. That is common to both of those events. So that would be A and B. However, A or B is just all the elements either in A or in B. So if we're using the exact same example, it would be all numbers, 2, 4, 6, 3, 6. All those numbers will be part of this set now, as opposed to just being 6. Next, we have complement. So complement is just the list of outcomes that are not in that particular event. So for example, let's just say I'm finding what probability of a not is. It will just be any outcomes that are not part of A. And then we have this null set, or the mutually exclusive sign. So it just indicates that there's nothing in common. So for example, rolling an odd number and rolling an even number on a six-sided die are mutually exclusive events because we can't end up having any outcomes that sort of conform to both of those events. And next we have ellipsin. The ellipsin is used as a symbol to indicate the entire sample space of a random experiment. So usually you will see the symbol in Venn diagrams, sometimes Carnot maps, usually not, but yeah, so definitely in a Venn diagram. Okay, so here we have just a quick example question. So we have probability A, event A, and the sample, and the outcomes are 1, 3, 5. B is 1, 2, 3, 4, and the sample space is 1, 2, 3, 4, 5, 6. So we have to list the following set. So what is A and B? So A and B is just going to be, what are the common things between elements A and B? So definitely 1 and definitely 3. So therefore the answer here is going to be 1 over 3. Now if we were to determine the probability of A and B instead, probability is, we'll come back to that in a second, but it's just how many, successful outcomes or favorable outcomes there are over the total number of outcomes. So therefore probability A, so what are the favorable outcomes? That's just going to be 1 and 3. So therefore there's 2 favorable outcomes over the total number of outcomes, which is 6. So therefore the probability of event A becoming true is going to be 1 over 3. Now if we look at A or B, that just gives you all elements that are in both A or B. So it can be, either an A just by itself, B by itself, or both common elements as well. So in this case, it will be 1, 3, 5, 1, 2, 3, 4. So all of these numbers. And lastly, we have A dash and B. So what this means is not A, that's how I read it, and B. So essentially, we're just looking at values that are just part of B and are not part of A. So we've already determined what A and B is. That was 1 and 3. So we're determining values that are just in B. So it can't be 1 and 3. So it'll just be 2 and 4 as our answer. So just elements that are part of B that are not part of A. Okay, so now we'll look at the fundamental properties of probability. So what is a probability in the first place? So the probability of an outcome occurring or an event occurring is just the number of favorable outcomes over the number of total outcomes. So that's essentially what the probability essentially means. And probabilities usually have, so since there's sort of like a chance sort of way of determining, the chance of something occurring, they are usually between, or probability of something is usually between 0 and 1, where 0 means impossible and 1 means certain. So, so you really need to know this formula, that any probability will be between 0 and 1. And another thing they need to know about is that the sum of all the outcomes, or the probabilities of all the outcomes, is always equal to 1. So the probability of getting 1 is, probably getting 1, probably getting 2, probably getting 3, probably getting 4, probably getting 5, probably getting 6. In a, when you roll a 6-sided die, when you add them all up together, it's going to be equal to 1. So essentially, the total probability is always equal to 1, and individual events are always between 0 and 1. So Venn diagrams are a really graphical way of representing probabilities. So we can visualize the sample space through a Venn diagram. So what we might do is we will have a box with the ellipse symbol inside it, and we will have 2 events. So one of the circles represents one event, one of the other circle represents the other event. So here in this case, we have A and B. So what we do is we put in elements. So let's just say we're rolling a 6-sided die. Event A is probability of getting an even number. Event B is, let's say, getting a multiple of 3, for example. So even number. So we have 2, 4, 6. What about event B? We have 1. Oh, sorry, not 1. We have multiples of 3. So we have 3, and we also have 6. Anything that's common, that's both of them, that's in both of them, we actually put it in the middle. So 6, we won't write it separately. We will actually put it in the middle. Like so. And any events that are not part of any of these events actually go outside. So 5 would be a number that would be outside this. So a Venn diagram is really good because depending on what we're trying to find out, we can sort of easily determine. So let's just say we're trying to determine what event A is going to be. So event A will just be this shaded region over here. So however many values you have, or sometimes it's also written as probability. So instead of being written as 2 over 4, sometimes it might be just written as 1 over 3 or something along those lines. But most of the time you'll get individual entries like so. But yeah, so you can easily determine certain probabilities just by looking at where those events are located. So if you're determining just event A, it will just be this shaded region over here. If you're determining event A and B, it will just be this mutual region between A and B, which accounts for all events or all outcomes that are part of both A and B at the same time. If we're determining the probability of event A not and B, so just event B, essentially we're looking at all elements that are part of B which are not part of A. So that will just be all of these. So essentially we're just removing the intersection between A and B. Next, if we're looking at A or B, we're essentially just looking at all of this entire shaded region. So that will give us event A and also event B. We also have an additional probability formula. So if we want to determine probability A or B, and we know what probability A is, probability B is, and probability A and B is, we can use this formula. If the if the Venn diagram is not mutually exclusive, which we'll look at in the next slide. So this formula can allow you to determine probability A or B, or probability A and B, if you are given the rest of the values. So really powerful formula that's usually given in your formula sheets, but otherwise you do definitely need to know how to use and sort of apply this formula. Okay, so next we have mutually exclusive events. So mutually exclusive events, not to confuse with independent events, is basically when we have events that cannot occur at the same time. So for example, it's raining and being sunny at the same time, although that sometimes does happen. But in the general sense, it's raining, complete thunderstorm, and also being, sunny is, a mutually exclusive. You're not going to get that happen at the same time. So these events are actually called mutually exclusive events. So this is how a Venn diagram would look if you had two mutually exclusive events. So as you can see, there are no intersections between these two graphs, so just like two discrete circles. So we can also have Venn diagrams with 3 events instead of 2. So these even become a little bit more complicated. But essentially they function in the exact same way. So this region over here in the middle represents outcomes that are part of both F, G, and H. This part represents only events that are part of F and H and not G. This just part of F and G, and this just part of G and H. So let's have a go. So we're looking at these probabilities. So probability F will just be, all of these values. So how many favorable outcomes do we have? So in total, we have 20 outcomes. So that's why that's in the denominator. But the number of favorable outcomes, so the probability of 6, is just going to be 6. So therefore, the probability of F occurring is going to be 6 over 20, which is 3 over 10, which is 0.3. Now, if we look at probability of G, that also has, so if we just count the number of favorable outcomes, that is going to be 8. So therefore, now it's going to be 8 over 20, which is 2 over 5, which is 0.4. Next, if we look at probability F and G, what we need to do for this one is look at what are the outcomes that are intersecting, F and G. So F and G. So we only have one outcome, which is 3, intersecting both F and G. So therefore, the favorable outcome is 1 over the total outcomes, which is 20. And F or G will essentially look at all of these values. So anything that's inside G, anything that's inside F, which is going to be 13 over 20. So it's just excluding these values over here. But the rest will be included. So yeah, so pretty straightforward. These probabilities is, you're going to get questions on these, and you should be able to do them fairly easily. So another sort of thing that a lot of students get confused with is the concept of conditional probability. So conditional probability is essentially where we know that something is occurring already. So let's just say we know that it's raining already, and I want to determine what's the probability of me using an umbrella, for example. So if it's raining already, obviously my chances are going to be, my chances of using an umbrella are going to be much higher as opposed to if it's not raining. So in this case, what I'm trying to determine is probability of using an umbrella given that it's already raining. Because if I was just looking at the probability of me using an umbrella, it's going to be a very low probability because, it doesn't rain quite often. So therefore, finding the probability of me using an umbrella given that it rains is going to be much higher. So that's essentially what conditional probability is. We're looking at the probability of something occurring if we know that another event has already occurred. So here is the formula. So probability A given B is equal to probability A and B over probability B. Yep, so just a formula that, you just have to memorize or have it written down somewhere. Usually it will be given in formula sheets as well. So for example, if it has rained the day before, there is usually a higher chance that it will rain the next day. If a card is drawn from the deck is black, there is a higher chance that spades is before. So here we've kind of a few scenarios of conditional probability. So in the first one, the condition is that it has rained the day before. In the second one, the condition is that the deck is black. So another useful way of displaying probability information, as opposed to Venn diagrams, is a Carnot map. A really, really good and useful sort of way of representing probability. So usually it's only used for two events. So we have probability A, probability not A, probability B, probability not B on the horizontal and vertical sides. And then in the gaps, we have these specific probabilities written down. So whenever we're finding an intersection, so the intersection of A and B, we're just doing A intersection B. So intersection of B naught and A will be A intersection B naught. Intersection of A naught and B will be probably of A naught and B. And so on and so forth. So this is really good. You can either write the number of outcomes that are present. So instead of doing probability, you can either also write N, or the number of events that are in A and B, or you can just write the probability. So so depending on what the question is, you'll be using various different methods. So we'll do our practice questions just to get sort of familiar with what this sort of represents. So the probability that Cynthia walks to school and it is raining is 0.1. So let's just draw up a Carnot map. So we have raining, not raining, walks, does not walk. So this is essentially how you have to set up your table. And remember, the total probability is always equal to 1. So the probability that Cynthia walks to school, so walks, and it is raining, so raining as well, is 0.1. So therefore, 0.1 will go here. The probability that it doesn't rain, so no rain, is 0.6. So just probability of no rain. We're not looking specifically for walking to school or not walking. We're just looking at the probability of not rain, which is 0.6. So essentially, these two gaps should add up to give you 1. So therefore, this is 0.6. So therefore, this must be 0.4. And this should add up to give you 0.4. So therefore, this must be 0.3. So that's how the Carnot map is so useful. We can use information that we're already being given to easily find other pieces of information that we might need. Using a Carnot map, what is the probability that on any given day she doesn't walk and is... the probability that she doesn't walk and is... not walk and it is raining. So essentially, we didn't even need to fill out the rest of the table. So she doesn't walk and it is raining is just going to be 0.3. So essentially what we're determining here was the probability of raining and not walk, which in this case is going to be 0.3. So pretty straightforward. If you know how to use a Carnot map, you should be pretty, pretty familiar with how to use this. So if it is raining today, so this is how the questions are going to start if it is a conditional probability question. So they're going to give you a condition first. It is raining today, so that's the condition. What is the probability that Cynthia walks? So now instead of finding probability, what is it raining and she walks, we're finding what's the probability that she walks given that it is raining. So essentially we just have our formula, so probability walking given rain. We put it into the formula. probability W and R over probability R. Pretty straightforward, just looking straight from the Carnot map, we easily get our answer. So pretty straightforward. Again, let me know if you have any questions. So next we have the independent probability formula. So events, so we can have events that are independent or dependent. Independent events are basically events that don't really have an impact on each other. So an example of an independent event would be flipping a coin and the probability that it rains tomorrow. So regardless of whether you get a heads or a tail, it shouldn't really impact whether it rains or doesn't rain tomorrow. Similarly, however, a dependent event might be something along lines of it raining and you using an umbrella on a particular day. Because yes, if it is raining, you are more likely to use an umbrella. So that's a dependent event. An independent event should not have effect. And there's a formula to confirm if something is an independent event or not. So essentially, probability A and B is going to be equal to probability A times probability B if it is an independent event. So essentially, a lot of these questions are going to ask you to prove that something is an independent event. And the way that you should go about doing this is, looking at what probability A and B is, what's given to you, so what probability A and B is given to you, and then finding out your own probability A and B, and if it matches, then it is independent. If it doesn't match, then it's not independent. Okay, another graphical display of probability is the tree diagram. So basically the way that the tree diagram works is it sort of shows the conditional probability. So the way that we do is we have two events occurring in a sequence. We can have two events or three events occurring in sequence. And it can actually be used to represent both dependent and independent events. So we have probability A. So we write the probability of A, above here. And therefore the probability of complement of A is just going to be the opposite. So 0.4. And then we go along, we find the probability of a B, probably a B naught, probably B naught, and so on and so forth. So I'm pretty sure all of you will be very familiar with how to use tree diagrams. Otherwise, do let me know if you have any questions, but we'll move on to a practice question. But just before we do that, I'd just like to remind everyone that if we are finding the probability that this happens and this happens, essentially what we do is we multiply the probabilities. So let's say we're trying to work out what's the probability that B given A occurs and B not given A occurs. Essentially we multiply. Oops. Yeah, so what's the probability that B occurs and A occurs? We just multiply this. So we multiply the probability of A multiplied by the probability of B to get probability A and B. But if we were determining the probability that something happens or something else happens, we add all the probabilities. So I'll explain what I mean when we do this example. So in Blair's will, if it rains the previous day, the chance of rain today is 0.6. If it doesn't rain the previous day, the chance of rain today is 0.3. Using a tree diagram, if it rains on Monday, what is the probability that it rains on Wednesday? So it has already rained on Monday. So for Tuesday, the probability that it rains is going to be 0.6, as given in the question stem. Therefore, the probability of not rain on Tuesday is going to be 0.4. And then going along, if it has rained on Tuesday, the probability of it raining on Wednesday is going to be 0.6. However, the probability of it not raining on Wednesday will be 0.4. And then for Wednesday, the probability of it raining, if it hasn't rained on Tuesday, is going to be 0.3. And the probability of it not raining is going to be 0.7. So again, just like an application of the tree diagram, you really should be familiar with drawing a tree diagram based on some information in a question stem. Now the question is, there are two outcomes that result in rain on Wednesday. Here's the question. What is the probability that it rains on Wednesday? So there are actually two outcomes for whether it rains on Wednesday. So the first outcome is rain on Tuesday, then rain on Wednesday, or rain on Tuesday and rain on Wednesday. So this is what I mean by or. So what is the probability that it rains on Wednesday? So we what we're trying to actually determine is the probability that it rains on Wednesday given that it has rained on Tuesday, or what's the probability that it rains on Wednesday given that it hasn't rained on Tuesday. So essentially what we would do here is we would determine what's probability of rain on Tuesday and rain on Wednesday. So 0.6 times 0.6, which is equal to 0.36. Then probability not rain on Tuesday and rain on Wednesday, which would be 0.4 times by 0.3. Just looking at this stem if you're confused, which is equal to 0.2. And if we're finally determining the probability that it rains on Wednesday, we can just add these two up together because both of them involve raining on Wednesday. So that will just be 0.36 plus 0.12. So this is where we have both and or in interplay. Okay, so next we'll look at combinations. So combinations is basically where we're trying to determine favorable outcomes when there are so many favorable outcomes. So let's just say we have a group of 50 students and we're trying to pick, 8 students to, represent. We can have so many combinations or so many different ways in which we can sort of perform that particular, application. So there's so many ways that we can select 8 people from 50 people, and therefore we'll have millions of outcomes. So instead of counting all of them, because that will just not be practical at that point, we use something called a combination. It's just a fast way of calculating favorable outcomes or the number of total outcomes when we know certain pieces of information. So for example, so this is here the formula. So n choose r, or also written as this sometimes. So essentially the formula NCR is actually this in actual mathematical terms. So the n is the number that you're choosing from. So the sample size, or the group size, and r is how many you're choosing, or how many successful outcomes there are. So for example, if you're choosing 8 people from a group of 50, n will be 50, and r will be 8. So then you put it into this formula, or in your CAS, I'm pretty sure there should be a function where you can just put this NCR straight away. And if you do that, you should get your final answer. But if you have to do it by hand, which you usually won't be, you can use this formula. You don't really need to know why this formula sort of works. It's just sort of, beyond the course. But yeah, so really important to just, know the formula and be able to apply it and know when to use the formula as well. So for example, if you need to get 4 questions right out of 5 on a test, 5C4 will tell you how many different ways you can pass. You might get the first question right, second question right, third question right, fourth question right, or you might get the second question right, third question right, fourth question right, fifth question right, or you might get the first question right, third question right. So many different ways that you can do this. So this will simplify that entire process and, solve it for you. So if you're confused about the symbol, the exclamation mark, it just is a factorial. So what that means is, if it's 5 factorial, it's just 5 times 4 times 3 times 2 times 1. So it's basically multiplying that number by all the numbers that come below it, sequentially. So here was just a quick example. So if a coin is flipped 7 times, how many different outcomes are there when 3 heads are flipped? So basically, n is going to be 7, and 3 is going to be r. So we just put this into the formula, and we should get 35 as our answer. So again, let me know if you have any questions in terms of this formula, but otherwise it should be pretty straightforward. Okay, so now we're actually done with the question. Sorry, not the question, the content for today's lecture. I'd just like to spend a few minutes just going over the exam, because I know many of you will be, starting to prepare for year 12 or a little bit overwhelmed, by what's coming next year. And if that's the case, I'd just like to, ease it a little bit. Whatever knowledge content you've learned today, and as well as, throughout the year, year 12 will just build on that content. So if you have your foundations really clear, there's a lot less effort that you will need to put in, next year. So don't neglect year 11 content. It's really important and will actually, severely impact you and your overall performance next year. But just in terms of your exam at your school, although it is up to your, up to the discretion of your school how they would like to structure your exam, you're likely to expect an exam 1 worth 1 hour, which is no notes and no CAS, and it's usually worth 40 marks, and also exam 2, which is 2 hours, and you're also allowed notes and a CAS, worth 80 marks. So although year 11 doesn't technically count towards your VCE or your ATAR, you should still be revising hard, and you should be preparing yourself, on the level of, effort that's required to be put in, in order to do well in your exam. So don't neglect your exams, really focus on it, try to put in as much effort as you would, next year. Another question a lot of students will ask around this time is how should they start preparing for Unit 3 for methods? Well, you should start preparing for Unit 3 for methods by, really being diligent with, your year 11 content. Really understanding all the concepts, being able to apply them. If there are any doubts or any uncertainties that you may have in your knowledge, really asking your teacher, getting all that cleared off before you go into year 12, so that you're ready to build on your knowledge as opposed to, having a really weak foundation and working on that foundation next year. Study smart, study hard, stay organized, ask for help, all those general things. Learn your CAS, I would probably say, is one of the more important things. Know how to do certain functions of CAS. Obviously, next year you're going to learn a lot more CAS sort of stuff, but this year just get familiar with all the basic sort of stuff, deriving, anti-deriving, defining functions, probability, stuff like that. And in the exam, if you do have an exam this year, which most of you will, and if it's in a very similar structure to the VCA exam, don't waste your times on questions that you do not know how to do, and use your reading time very effectively. So that's just some of the basic tips that I had for, starting thinking about Unit 3 for methods, and also how to, start preparing. Otherwise, if you have any questions, please swap them through into the chat. I'll be monitoring the chat for a few more minutes. Otherwise, thank you everyone for coming to today's lecture, and I hope you all the best for the rest of the year. And if you're doing any 3-4 subjects, good luck for that. See ya.